Good day, my name is Mubarak Adetunji Ojewale. The title of our work is Multi-Level Preemption in TSN, Feasibility and Requirement Analysis. The other co-authors on this work are Patrick Mimuyomsi from the Sister Research Center in Polytechnic Institute of Porto in Portugal, just like myself, and we have Borislav Nikolic from the Institute of Computer and Network Engineering in TU Braunschweig from Germany. Distributed real-time applications from the avionics to the automotive to multimedia streaming service all require predictable communication to function properly. Ethernet, Ethernet is becoming an increasingly appealing solution in the industry to achieve predictable real-time communication in these domains due to its bandwidth and cost advantages over previous communication technologies. However, real-time features were not part of the standard Ethernet designs, which necessitate the introduction of several patches in form of standards to introduce real-time features to Ethernet. This has led to many flavors of Ethernet for some of these domains, from the AFDX to AVB to TT Ethernet, and now to the latest set of standards on the topic, TSN. TSN refers to a set of new standards introduced to Ethernet to achieve real-time communication, both time-triggered and event-triggered. TSN enables predictable transmission of heterogeneous traffic over an Ethernet backbone network in embedded and distributed real-time embedded systems. Key features of the TSN standards include clock synchronization standards, time-triggered transmission, frame replication for reliability, path reservation and path control and resource reservation protocol, and last but not least, frame preemption feature, which is the focus of our work. TSN frame preemption standards, the IEEE 802.1 QBU and the 802.3 BR standards, specify the techniques for the interruption of the transmission of a less urgent frame for the transmission of a frame that is considered more urgent. In these standards, frames are categorized into two categories. We have the EMAC or express frames, and we have the PMAC from preemptable frames. And these categories are given with the following interpretation. Only EMAC frames can preempt PMAC frames, and frames from the same category cannot preempt one another. So to illustrate how these two categories work, we give an example of a preemptable frame that is already in transmission. Then EMAC frames arrive and they interrupt the transmission of the PMAC frame, and the PMAC frame transmission only continued after the transmission of the EMAC frames. Frame preemption, as specified in the standard, is implemented at the MAC sublayer, and it reduces the maximum lower priority blocking incurred by an urgent frame by up to 90%. And also the overhead cost of preemption is known, because this preemption comes at the cost of some overhead. This overhead cost is known and bounded. Roughly speaking, it is about the time taken to transmit 24 bytes of data. The major limitation of the frame preemption standard, however, is that it has just one level of preemption support. As we have explained earlier, frame can only be categorized into two categories: the EMAC frames we can preempt and the PMAC frames which have been preempted. And frames in the same category cannot preempt one another. We demonstrate this limitation in the next slide. So to demonstrate the limitation of the one-level preemption approach, we introduced two new classes of preemptable frames. So we have two type we have one with a timing constraint, which is represented in black in the black box, and and the preemptable frame without timing constraint at all, which is represented in the green box. So in our example, the green frame without timing constraints arrive first, and it begins in its transmission, but it is interrupted by an express frame, EMAC frame. But during the transmission, we notice that another preemptable frame with timing constraints arrives, but this frame cannot be transmitted under the one-level preemption scheme, as it has to wait for the complete transmission of the green cream frame. Remember, frames in the same category cannot preempt one another, and there are just two levels of preemption. There are just two classes of frame. So this continue even for the other arriving black frame, and they are only able to transmit after the complete transmission of the green frame. This kind of delay can be significant and can be up to 120 microseconds per hop, considering a 100 megabit speed Ethernet link. So to elevate the condition of this kind of frame, we propose a multi-level preemption scheme where there are more than two classes, where we are not restricted to just two classes of frame and one level of preemption. With this assumption, we can already notice an improvement in the responsiveness of preemptable frame. But the current standard specification of the current frame preemption standards do not support this kind of transmission. So in this work, our focus is to investigate the feasibility of the current, or the feasibility and the required changes to the standards, to support this kind of frame transmission. We will be investigating the feasibility of multi-level preemption under four headings. First, we check the frame format if they are sufficient for this kind of transmission. Next, we proceed to the preemption service interfaces, and then we investigate the required modification to the frame transmission and reception processes themselves. To start with the frame format, on the screen is the typical MAC Ethernet frame format. We found out that the start frame delimiter value is used currently to distinguish between the categories of frames and also the fragment of frames. By fragments, we mean that when a preemptable frame when preemption occurs, a preemptable frame is broken down into a start fragment, zero or more continuation fragments, and then a final fragment. So the SFD value is used to distinguish between the express frame, the preemptable frame, and fragment of the preemptable frames. So currently there are just 11 values defined for the SFD. We believe that by enriching the SFD value definitions in the standards, we can enable the Ethernet switches to recognize more than just two classes of frame and more than just one class of frame fragments. And this is with this, we'll be able to achieve multi-level preemption. Also, we'll go to the MAC match sublayer service interfaces. Recall that we mentioned that frames in the same category cannot preempt one another. In practical sense, this is because a MAC match sublayer service interface cannot preempt itself. And for each additional level of preemption to be added, that means that MAC match sublayer interface. So our finding indicates that we can achieve multi-level preemption by adding more MAC match sublayer interfaces. Now to the frame transmission and reception process. Before frame transmission and reception, according to the current standard, there is a process known as the verification process. In this process, the sender communicates with the receiver to know if the receiver supports multi-level preemptive transmission or not. Only after this confirmation does preemptive transmission occur. Under multi-level preemption, in addition to verifying whether the receiver supports preemption or not, the receiver also gives a feedback to the sender on the level of preemption it supports. This is critical to the multi-level preemption paradigm. So after the verification processes, then the transmission begins proper. In the event that the preemption does not occur, the multi-level preemption switch behaves just like this one-level preemption switch or the non-preemptive switch at all. But when preemption occurs, we describe now the behavior of a multi-level preemption sender and receiver node. So first, to illustrate what happens under a multi-level preemption scheme, we consider three sets of frame as our motivation example. The green one is lowest priority one without timing constraints. The black one is a preemptable frame with timing constraint, and the red frame is an express frame. Also, we consider that each of these frames are broken into the fragments that we have introduced earlier. Each of the preemptable frames are broken into fragments. So, and also we zoom in into what happens in the receiver. The receiver contains input buffers where frames are received, processed, and rearranged, and also the output buffers where the output queues where frames are queued for onwards transmission to other nodes. So under the multi-level preemption scheme, what happens is that when the green frame starts its transmission and the black frame arrive, unlike the one-level preemption scheme, the black frame does not have to wait for the green frame, but it preempts the green frame, and just after the preemption of the green frame, the red frame arrives, and when the red frame can also preempt the black frame. So this is what we are talking about. So we also notice that after the complete transmission of the express frame, unlike in the one-level preemption scheme, instead of the green frame to resume, the black frame will resume first, which is the frame with frame timing requirements, before the green frame with no timing requirements resume. We also note that frames are rearranged, the fragment of frames are rearranged completely in the buffers before being sent into the output queues. To achieve the kind of frame transmission and reception that we have described, a lot of modifications are required in the frame reception and frame transmission processes as specified in the standard. This we have detailed in our work. Also, we commented on the frame buffering requirements. We especially noted that each of the frame classes requires at least a unique input buffer for us to be able to correctly reassemble fragment of a frame and forward to the output queues. Also, interoperability with one-level preemption switches and non-preemptive switches is guaranteed by the verification process, in the sense that the receiver is able to tell the sender whether it supports multi-level preemption, one-level preemption, or non-preemptive switches at all, and this guarantees interoperability. Finally, in the experiment session, we demonstrated again delimitation of the one-level preemption scheme experimentally by using 3 flows and assuming 2 levels of preemption. The network consists of 6 node and 2 preemptive switches, and the frame properties are as presented in table above. 2 batches of experiments were conducted. In the first batch of experiments, we left F1, which is an express and IMAC frame, only on the express interface. And in the second batch of experiments, all time-sensitive flows, both express and both IMAC and PMAC, shares the IMAC service interface. In the results, we notice that in the first instance, where F1 enjoys exclusive right access to the EMAC service interface, it was able to meet all of its deadline, but F2 could not meet its deadline because it is in the PMAC interface and it is being interrupted by a best effort flow F3. But in the second batch of experiments, when F2 is moved to the EMAC interface, F2 is now protected from best effort stream and is able to meet its deadline, but at the cost of F1 now missing its deadline in some of the instances. But by assuming a multi-level preemption scheme, F1 and F2 are able to meet their deadlines conveniently. In summary, in this work, we have highlighted the limitation of the one-level preemption scheme, and we have presented in details a multi-level preemption paradigm. The details of the feasibility and implementation requirements of this paradigm are presented, and we also commented on the buffering and interoperability requirements for multi-level preemption. Finally, as future work is ongoing on the implementation of the multi-level preemption scheme on a simulator, and the associated worst case timing guarantee is being investigated. Thank you.